So you are able to see the screen, no?
Yes, sir.
Okay, so anyway, we will start our discussion. So last class, if you remember, so we have almost, whatever are the commonly encountered random variables. Okay, so like you see, normal we have seen. So normal, if x is normal, say, then if you take some y is equal to e to the power of x, you get log normal. If you square, you will get chi square. Then the ratio, say, like this type of thing, you will get student distribution, t distribution. Then f distribution, Cauchy's random variable. So this is a pathological the distribution. It's a very special distribution. So exponential. So like this, so these are so many are there, but these are the things which are widely used in practice. Okay. So then finally we came to two-dimensional random variables also. Like if we are having a two-dimensional problem, say, so like you see, two separate random variables are there and they may be interlinked also. Then how do we construct this probability density? So first we have done this discrete. Okay, so like you see, we have taken a typical example like 139 students, how much time they spend and their productivity, say. Of course, you can do this as independent also, like duration is no way connected to productivity, say, okay, that also one can do. But if these two are interlinked, okay, because how much time you spend, how much is your productivity, they are all very interlinked. So how to construct the probability densities? Okay, so now like one dimensional you have a histogram. So when you are doing two dimensional, say, so you have to take all possible combinations, okay, like 6 comma 50, 670, and then you find out how many students are falling in this each group, and then you can construct. Since it is a discrete set, you have to write everything in terms of direct delta functions. So and then you can construct this px this y. And as already I told you, our notation say will be like this. So px is equal to x, y is equal to y. We write comma operator basically. So this comma operator anyway, it indicates intersection. Okay, that is the meaning of this expression. So these are how the joint distributions, the joint densities you can construct for discrete cases. Now if we sum up our row and column, what do we get? No. Like last class I told you, right? So this is a two-dimensional, the probability function is there. So here, you can sum over x. So summing up over the row or summing up over the column basically. Okay, so you get their one-dimensional densities. So if you sum up over duration, say, you will get productivity. If you sum up over productivity, say, you will get this duration. So you can obtain this marginal densities, or these are the one-dimensional things also. So this is what we call as the marginal densities also you can construct from this distributions. Okay, so this I have explained you in the last class, and then you can do a lot of interesting things. Okay, conditional thing and other thing also. So now finally, say, now let us look at this the continuous random variables. Say, how do we write this one? Okay, so there are continuous 2D random variables. So now here also, it's very straightforward because, so like you see, if we are having two random variables or two events basically, okay. So one is a capital X less than or equal to X, and then we have another event to say, okay. So some capital Y less than or equal to, the Y, like for example, you see the compressive strength of concrete, and maybe the water content, or maybe temperature, or which are highly interlinked kind of thing. Okay, so now we are looking for an event E which is intersection of these two events. Okay, so this we write as capital X less than or equal to X, intersection, say, capital Y less than or equal to Y itself. Okay, so this we call this as in intersection, say, we replace our intersection with comma. So this is just to simplify the notation, we write like this. So generally intersections are replaced with comma operator. So now this is what we call as the joint, the probability. So now to characterize this, we write this a joint, probability distribution function. So which is, two things are. So this is a joint probability distribution function. So which is written as, like this. So capital P x y small x comma y. So this we write as x less than or equal to x, capital Y less than or equal to y. So this is how we write our the probability distributions, the functions. The same fashion, whatever I showed you the example, say it is a discrete, now it may be continuous. Okay, so now similar fashion, say we can write the joint density also. Okay, so the joint density, now how do you get density function for distribution? What's the relationship between probability distribution function and probability density function? Now, what is the relationship between distribution and density? So like probability distribution is given to you. So how do you compute density? For given density function, say, can you compute probability distribution? No.
By differentiating probability distribution function, we can get probability density function.
No. So there is a derivative. Okay. So there's no. So now pxy. Okay. So the joint density function, say. Okay. So this will be, you know. So that so now here it is 2 dimensions basically. So if it was 1-dimensional random variable, say, we wrote in terms of you know, the ordinary difference. No. So now density function, so because it is a 2-dimensional thing, so what happens is you will have a partial derivative. Okay. So pxy, you know, x comma y by using dou x dou y. Okay. So this is a joint density function. So only difference between the 1-dimensional and 2 dimensions is there you are having ordinary differential equation, you know, the derivative, but here you have partial differential equation because you know you have this 2 variables are there. And now let us see the properties. Okay, so properties of density function, of course, as well as you know, the distribution function, say 2 dimensions. Now in 1 dimension, say we had a, you know, a curve kind of thing. So now in 2D, how the densities will look like? So basically it is a surface kind of thing. Okay, so the everything becomes a surface because you are looking at in 2 dimensions. So it is something like this, you know. So we have a capital X, capital Y. So 2 dimensions are there. So your distribution function, if you try to plot, you know, something like this, it will be, you know, the area under the surface or whatever, you know, like this. So it is basically a 2-dimensional kind of quantities we have. Now another important property is the capital Pxy, so which is a distribution function. So what is this value? Infinity comma infinity is equal to So this is our probability, you know, the distribution function. So when I write infinity, say, so what is an expression, this one? X less than or equal to infinity and capital Y is less than or equal to infinity. Now what is the value? What was in 1 dimension? What was Px of infinity?
One.
No, it is 1. So in 2 dimensions also it will be 1 itself. Okay, more or less same as 1 dimension, but it will be 2D here. Now similarly, say, now what is a capital Pxy? Okay, minus infinity comma, you know, infinity. Now what will be this value? Now this one. Now what will be this value? So everything minus infinity. So
0.
It will be 0. Then you know what will be Pxy? Minus infinity comma y. What will be this value? So this means probability x less than or equal to minus infinity, but y, you know, less than or equal to y. What will be this value? Now what will be this value? It is in 2 dimensions. Now x is you know, still at minus infinity, y is varying. Okay, so basically what will be this value?
Dy.
No, it will be 0 only. Okay, so you can verify and you can check also. Okay, now similarly, so Pxy, so x comma minus infinity. Now this also will be see minus infinity to comma y. This also will be 0 only. Okay, then you see Pxy, say, so the density function, the derivative x comma y. So we have we have written like this. Okay, so if we have the density function, so minus infinity to x, so minus infinity to y. Okay, so p xy x comma y dx dy. You followed. So this the relationship anyway, the same thing only. Now another most important thing also what we have seen is this marginal densities. Okay, so when you integrate over one side, so the marginal the density. See, like for example, our marginal density or marginal distribution basically. So if you get from probability density, you will have marginal density. If you write from distribution, so you will get like this. Okay, so Py of y. So this is defined as minus infinity to infinity, and this will be minus infinity to y. So Pxy x comma y dx dy actually. So this is the marginal distribution is defined like this. So here what are you doing? See, original integration, if you see say from the density function, so it is basically minus infinity to x minus infinity to y basically. So this is the joint the distribution function. Now what are you doing if you want the marginal distribution function for y say? So you have to integrate x from minus infinity to plus infinity. So obviously in one direction say you are integrating everything, or we have seen, right, you are summing up all the rows or columns or whatever. So what happens is you will get the one dimensional distribution. Now similarly say if I want px of x, what is that I have to do? Now, so what we have to do now? So px of x. So what will be my limits?
Minus infinity to x, and y will vary from minus infinity to infinity.
Minus infinity to plus. So you integrate everything. This y and x thing, you keep it open. So then you will get marginal, the distributions also. And of course, you can find out the marginal densities also. Like you see, if I want a density function, say, so this will be simply the derivative. Okay, so dpx of x by dx kind of thing. And then r, you can also write this as it's a minus infinity to plus infinity. So we have pxy is x comma y dy. Okay, and then the py of y, say in similar fashion, you can write so dp capital Y of y by dy, and you have this integral minus infinity to plus infinity. So pxy x comma y. Now you integrate over dx. Okay, so this also you can write the distributions as well as the density functions. So these are the marginal the one-dimensional things which you can get from here. Now another, so now here the most important thing, if you find out here say, so now if pxy is given to you, okay, so pxy if it is given now, so you can obtain the densities. So px comma x, py comma y, this can be calculated or this can be obtained. Okay, but suppose say let us I have only one dimensional thing, so I have only these densities, individual density functions are there. Can I construct pxy? So whether this is possible, say given px comma x comma y, if I integrate over row and if I integrate over a column, I can get the individual densities or distributions. But now if I ask these questions, I know the individual probability densities are the individual the distribution functions. Can I construct a 2D from this data or from these two distributions, whether this is possible? Now whether
No.
this is it is not possible. You followed, right? So this is not, of course, it may be possible for some special cases that we will discuss after some time. But generally, from two dimensions, you can come to one dimensions. But knowing the one-dimensional thing, you can climb up. You cannot climb to the higher dimensions. Okay, so this also is a very important. But this reverse is possible. That it is not that it is impossible kind of thing. This is possible. Only special case. Okay, so I will write here later also that special case. What will be that special case? Can you guess when it is possible? See, we have discussed previous.
When they're independent,
Whether independent. See, we have discussed a probability of A intersection B, say. If A and B are independent, how do you write that probability of A intersection B? You can write as?
probability of A into probability of B.
Probability of A into probability of B. So now if X and Y are independent, say. So what will be Pxy X comma Y? If A are independent, it will be? Now, what will be that one? Suppose if they are independent, say, so the two dimension, what is comma operator? As already I told you, comma indicates what?
Intersection.
Intersection only. Okay. So now you tell me what happens if x and y are independent. So what will be pxy x comma y? It can be written as
Probability of X, probability of Y.
multiplication of these two. So this is a possible. Only special case is the independent. Okay, that x and y has to be independent, then only it is valid. But if they are dependent, then no way, you cannot construct the two dimensions from the one-dimensional data. So this also is very important property. And of course, this is straightforward. So if I want to find out the probabilities, like you see x less than or equal to x2, okay, comma, y1 less than y less than or equal to y2, say. I want to find out the probability that x lies from x1 to x2, y lies from y1 to y2. So this I have to find out the area under the probability density function. The limits will be like this. So y1, y2, so pxy, x comma y dx dy. So this integral has to be performed actually, okay. And now of course the independence property we write. So the independence, so we will prove it here. So the independence of random variables. So if I have two random variables, x and y, and let us say they are independent. So in mathematics, in probability theory, we use this operator. Okay, so this is a symbol. This symbol means independent. So generally in many textbooks, they say if x is independent of y, say they will be using this type of symbol. That means this symbol indicates, you see, like comma indicates intersection. No? Independent means this type of symbol is used here. So now when the things are independent, say, so pxy, that is a joint, the distribution function, the capital. So this becomes, x comma y, and then you see x less than or equal to x, then y less than or equal to y. So finally this can be split into, two pieces actually, x less than or equal to x multiplied by, you see, p of y, capital Y less than or equal to y, or the joint density. So this is a distribution, but the density function also, say, I can write as a product of px of x multiplied by, you see, py of y itself. So this is a very important property, the independence, you see, when things are independent, say, so it will be like this. Okay, and now conditional probability also we can write. So the conditional, the probability. Now here also, like you see, if I want the probability of y less than or equal to y given x less than or equal to x actual. So now you tell me what will be this value. What is the probability of a given b? Previously we have written, right? What is that? What is the probability of a given b?
Probability of y itself.
No, if they are not independent, okay. So assuming, of course, what you told is fine, but a and b are not independent. They are dependent only. Then what will be probability of a given b? If they are independent anyway, this will be same as a p of a only. But if they are dependent, so what is that you write?
P of a intersection b divided by p of b.
So what is the p of a intersection b by p of b, say? And now you relate to this one, say. Okay. So now what will be p of a intersection b? So that what will be in the numerator? No. So what will be in the numerator here? So what will be the numerator essentially?
Probability of y comma x.
Y comma, you followed, right? This one divided by, you see, x less than or equal to x. So what is the numerator? Numerator is nothing but the joint. The joint distribution itself, whatever we have written, say, so divided by its marginal, the density distribution function. So it is something like the joint two-dimensional thing, whatever you have. So you divide by the, the marginal you followed. This one automatically will get the conditional probability. Now you can find out this is a conditional probability distribution, the density function, say. Okay, straightforward only. So py, this one will be pxy, sorry, x comma y divided by px of x also. So this also is an interesting, the property of two-dimension things. Now when you go to two dimensions, like similar in our one-dimensional, so if you want to characterize randomness, okay, one way is to write the distribution, densities and others. What is another alternative way we have discussed? So to characterize a random variable, we have said, right, instead of distribution densities, you can also write in terms of, now what are those quantities?
Some moments.
Movement. So now the movements, how do you calculate movements? How to calculate the movements? Well, which is the operator? How do we calculate movements? How you want, if you want to find out movements, the first movement or second movements, how do you calculate movements? What is that mathematical operator we used?
Integration.
The integration was fine. What did we call that one? You know that. You remember?
Expectation.
Okay, that is expectation operator. So now that was for one dimensional. Now here you are having two random variables. So now what happens is you will be having joint expectations actually. Okay, not one this one, and so this will be like this: g x comma y. So we denote like this: are expected values, say g of x comma y. So this is defined by this integral minus infinity to infinity minus infinity to infinity g x comma y. Okay, p xy x comma y dx dy. So this is the the joint movement or joint expectation and other things. So this is an expectation operator why we write for two-dimensional random variable. Now we will write the expression for movements. So now here also we can define movements, but there are two dimensions. So you will be having a two-dimensional thing. So it is defined like this: x to the power of n, y to the power of k. So this is how we define. So this expression you can write this as minus infinity to infinity minus infinity to infinity x to the power of n, say y to the power of k, pxy x comma y dx dy. So these are the movements. Now tell me, what is the movement 0 0? Now what is the value here? That is x to the power of 0, y to the power of 0. Now, what is the value?
Sir, it's 1.
Now, why it is 1? Because this will be 1, 1. Now, finally, it turns out to be, this will be x to the power of 0, y to the power of 0, that will be 1, 1. So, finally, it boils down to
Area under the probability density.
Probability you followed, right? The surface, it is not a function now. So, this is basically equal to 1. Now, what is m10? What will be this value? Minus infinity to infinity minus infinity to infinity. So x to the power of 1, y to the power of 0 anyway, this one, pxy x comma y dx dy. So what is this value? Now you tell me by just what is that you will get from this expression? So look at it carefully and then tell me what is the value.
So mu x.
Now, why it is a mu x? How did you get mu x? No, it is a mu x. What you told is correct only, but how did you get this mu x?
X. If I integrate the pxy x comma y, so that will give me 1. And
1.
then
It is 1.
Sir, only pxy integration of pxy.
No, your answer is correct, but your explanation is not, proper. See, what is this integral? See, only x is there, y is not there. You follow it. So now if I write this expression, say minus infinity to infinity, x I will put here, minus infinity to infinity, pxy x comma y dy into dx. If I write like this, the same expression. Now you tell me what is this integral? So if I am integrating my two-dimensional function across y, what do we get? What do we get this expression? If I integrate my two-dimensional function, it will be px. That's a marginal, the density you followed. So this will be simply x into px of x only will be there. You followed. So this will be, px of x. That is a marginal density. Now what will be this value? Now x into px of x, say already we have seen for one dimensional case, it is nothing but the mean value. You followed. So that is how you have to provide answer. Now in a similar fashion, so what will be m01? Tell me what will be m01?
Mu y.
Mu y. So the explanation will be same expression. Instead of x, you have to replace with y, say. So then with x you can integrate. So if you have integrated over x, say, okay, so you will get the marginal density function of y. So it becomes y into py of y into dy itself. So that means automatically it will be mu y itself. Okay. So this is a very the important thing, observations you can find out. Now like that you can find out so many movements you can create, but the you can do for x and y. So another movements what people generally use, interesting things will come when you use this joint central movements. That is after subtracting the mean values, like we also did for the previous case. Okay, so they are indicated by the eta symbol. Okay, n comma k. So this is x minus mu x whole to the power of n, and then y minus mu y, say, whole to the power of k. So these are the joint central movements basically, and it is denoted by this damping symbol we use right in our dynamics. So now this eta 0 0 you can prove it will be 1. Now what will be eta 1 0? So m10 was mu of x actually, okay, and m01 was mu of y. Now we have subtracted the individual movements from their values. So now what will be eta 1 comma 0?
So 0.
You can prove it, okay. So so eta 01 also will be 0 itself. And now we can find out what is eta 2 comma 2 0 actually. So this will be minus infinity to plus infinity, minus infinity to plus infinity. So we have x minus mu x whole square, and the other one is 0, so it will be 1. So we have pxy, okay, x comma y dx dy. Okay, so now what will be this expression? Tell me what will be the value of this one? It will be equal to what? It represents what quantity? It's the same concept you use for this expression. So how did we find out this one? So same concept you use here. What do we get here?
Sigma x square.
Sigma x square. Okay, obviously because you integrate over y, so you will get finally x minus mu x whole square px of x into dx only, which is nothing but variance of the x. Now similarly, say what will be eta 0 to now that means y minus mu y whole square. It will be simply sigma
y square.
Y square. So these are the one-dimensional things you can derive. And now the special thing is eta 1 1 actually. Okay. So minus infinity to infinity, minus infinity to infinity, x minus mu of x multiplied by y minus mu y, pxy, x comma y dx dy. What is this quantity known as? Any of you know? This quantity is known as, what is the speciality of this one, or what do we call this thing? Units are same as like this only. So this is a variance of x. You followed? So variance of x. Okay. So if you compare units, say eta 2 0, eta 0 2, they are all squares on, and eta 1 1, say the units are same. You followed, right? If x and y are in centimeters, say. So variance will be centimeter square. This also will be because x centimeter, y centimeter. Units are all same actually. So now what will be this is known as? Any of you know? This we call as
Covariance.
Covariance actually followed. So this is a very the interesting thing, the covariance expression. Now if I have so this is known as a covariance x comma y. Okay, this or sometimes this also is known as some sigma xy also, they write in the some textbooks. So this has a very interesting property. Suppose if I x plus, suppose I have added a constant to a, if to x and y plus b, I have added some constant. I have shifted my x-axis by some constant value a, and then y also have shifted by b, say. Now what will be the covariance of this one? So what happens to covariance? I have shifted my axis. The origin has been shifted. So what happens to covariance? See this expression and tell me. Covariance will change, or what happens to covariance? See, this is a covariance of eta 11 for x comma y. Now what I have done is I have shifted my axis, x by some constant a and then y by some constant b. Now what will happen to the covariance?
So it will remain unchanged.
It will remain same. You follow. So this is a most important property. Now another thing also you can prove yourself mathematically. So by this integral. Now suppose I multiply x by a and y by b say. Now what happens to covariance? Instead of adding, I have multiplied the whole x-axis by some constant a and y also by b say. Okay, so you can try. So you know a into what happens to covariance? Tell me. Look at this integral and then tell me. That's all. It's very simple. Now what happens?
AB covariance XY.
AB into covariance of X. That's all. It's very simple. Just look at the integral, substitute there. So what happens? A into x minus mu x, a into y minus mu y, pxy. So AB comes out. The inside value will be still covariance only. You followed. So like this, you know, you can have some interesting things also. Now another in practice, you know, covariance nobody uses or uses also, but sometimes the most popular one is a correlation coefficient. Okay, so this is the most widely followed, right? The correlation coefficient. So it is denoted by some symbol R, XY, or sometimes some textbooks they also use rho and other things also. Okay, so it is defined as sigma XY, say by sigma X, sigma y. So this is our correlation coefficient, and one can show mathematically that this correlation coefficient say always lies between -1 to +1. Okay, so this is a very important property. So you can prove this also. The maximum value cannot exceed plus or minus 1. So this can be proved like this. Okay, so sigma xy, as already we have said, minus infinity to infinity, minus infinity to infinity. Okay. So x minus mu x and y minus mu y, pxy, x comma y, dx dy. Okay, so this is my correlation. This one say. So now to prove this -1 and this one, you know, there is what we call as squads inequality. Okay, so there is you followed. What they call as this is squads inequality in mathematics. Okay, so if they say that if I have two functions, say f of x, then g of x dx. So they say that the squads inequality, if I have any integral like this, it will be always less than or equal to integral f square x dx whole to the power of half, and then g square x dx, okay, whole to the power of half. This is a famous squads inequality. So this is given in mathematics. Okay, using the same expression, say for sigma xy, I can write this sigma xy as the same integral minus infinity to plus infinity, minus infinity to plus infinity. I will write this expression as x minus mu x, say square root of pxy x comma y, and then y minus mu y. Okay, square root of pxy x comma y dx dy. You followed. So we write like this to say. So now so this is something like f of x. This is something like g of x. So now using the same squads inequality say. So this should be always less than or equal to I will write in the next page. So using the squads inequality, so this should be x minus mu x whole square pxy x comma y dx dy. Okay, so the whole to the power of half, and then multiplied by same thing. Multiplied by integral whatever. So y minus mu y. So pxy say x comma y dx dy. Of course, you will have the inside square will be there half actual. So you can see the squads inequality f square is there and g square is there. That's why that square root gets cancelled and x minus mu x will be there. Okay. So this is how the expression looks like. Now, what is the value of this inside the integral? Now, what is x minus mu, whole square pxy dx dy, and all the integrals runs from minus infinity to plus infinity. So, what is the value of this expression? The inside quantities.
Sigma x square and sigma y square.
Sigma x square, sigma y square. But outside, what is that you are having?
Sigma x and sigma y.
So square root is there, so that gets cancelled. So finally, sigma x, sigma y. Okay, so that means your sigma xy say always it will be less than the product of these two. So now rxy, what is the maximum value it can take? So rxy is defined as sigma xy by sigma x into sigma y. So now from squads inequality say. So what we are saying is the numerator can never exceed. See, the numerator can never exceed. Tell me what is the value? The maximum value it can take is
1.
So maximum value it can take is this one. So what happens is you followed, right? So this becomes it cannot exceed you see less than or equal to 1. So this is a very, very important property of this correlation coefficient. Now that why that plus or minus 1 comes also, we will see that one. Okay, so that is a 14 15. Okay, so suppose if I'm having x and y, say two random variables are there, and let us say y is ax plus b. Both of them are interlinked, or one are linearly related. This also is very important. Many times we fit this straight lines, right? So this is how it looks like. And now let us say x has the mean value of x is mu x, and the standard deviation is sigma x, and y also it has a mean value mu y and then sigma y. But we can find out, right, mu y is simple, you see, a times mu x plus b itself. Okay, and now sigma y square say, so you can easily find out y minus mu y whole square, the expectation operator. So if you substitute, so y is ax plus b, okay, minus a mu x plus b, this entire thing whole square, this one. So this b gets cancelled. Okay, so this turns out to be a comes out, a square turns out outside, and x minus mu x whole square turns out to be inside. What is x minus mu x whole square expectation? This is now what is x minus mu x whole square expectation of that one? That is same as that is same as what? Now what is this value? Expectation of x minus mu of x whole sigma x square only. Okay, so this is our sigma y square. Okay, now if I try to find out covariances of x and y, so that will be sigma xy. So that will be simply x minus mu of x multiplied by y minus mu of y. So here also you substitute, say, okay. So x minus mu of x will be there, and y anyway we have said, right, y minus mu of y, the b gets cancelled. So a turns out to be, so x minus mu of x. So this one will come. So finally say, so this to a you can pull it outside. So x minus mu of x whole square, this comes, and this is same as a into sigma x square. Okay, now if I try to find out the correlation coefficient, okay, so the numerator is sigma xy, that is a times sigma x square. Okay, and what is sigma x is sigma x, and what is sigma y? Sigma y is, this is sigma y square. What is sigma y? What is sigma y?
A times sigma x.
Be careful here, you have to be very careful here, because when you take a square root, say, okay, so the sign becomes very important. You followed. See, suppose this a, what will be this a? Suppose if a is minus 2, okay, so if they are negatively correlated, say, so sigma y square will remain whether a is a plus or minus, sigma y square will not have any effect. But when you try to find out sigma y, say, so this is square root, you have to be very careful. So that's why we write as a times this you see, sorry, this a, this one, so sigma x in this thing. So this gets cancelled. So finally we write this as, you see, a by square root of sorry, this No, this whole square will come. So finally say, so we will have this, plus or minus, the one kind of thing, it happens. Okay. So it depends on your, this square root also. Sorry, 1 second. Where is a times sigma x square? So then we have, yes. No, a times only, but finally say, so you will be having, this a, this quantity will be there. Okay, the square root issue will come. So because of the square roots, you will be having plus or minus 1 itself. Okay, so this is a very important thing which you have to remember. Okay. So now the things are so the maximum value or the minimum value, say this covariance or correlation coefficient can take is plus or minus 1. So that depends on your this one. Suppose if they are negatively correlated, say, so y is minus some ax plus b or whatever, so then the correlation may be negative, and if a is a positive, say, so it depends on the sign of this itself. Okay, so this also is a very important property of the correlation coefficient. And now let us one simple the example, we will see how to compute these numbers in practice. Okay, so let us 60. So let us say discrete random variable, we will see. So now I am having two random variables, very simple. One random variable is x, and the random variable is y. Okay, and these are a Bernoulli random variable. So Bernoulli means how many options will be there? So Bernoulli means how many this will be there?
Two outcomes.
Two outcomes will be there. So now let us say for x, say it has two outcomes. It can be 11 or it can be 17 actually. Okay, and y also has two outcomes. It can be 20 or it can be 8 kind of thing. So these are the two random variables, Bernoulli random variables. And the probability of getting 11 is 0.5. Probability of 17 is also 0.5. This also is 0.5. This also is 0.5. So these are the individual probabilities. Okay, to this one. Now what will be the mean value? What is the mu of x? Now, what is the individual mu of x? Tell me, what will be the mean here? Can you calculate? The first case, 11 and 17, 0.5, 0.5 is the probability. It will be? Now, what will be the this mean value? 11 and 17. Now, just you calculate 11 into 0.5 plus 17 into 0.5. What is the answer you get? See, mean we have said, right? X into px
14.
of x. It is 14 actually. Okay. Now, what will be mean value of y? Now, similarly, 20 into 0.5 plus 8 into 0.5. It is
14.
also 14 only. Very simple. Okay. Now, standard deviation, how much? What will be sigma x square, or the sigma x, say? How do you calculate? For this simple data. So you have to do, suppose if I want to calculate, say, so because it is x minus mu of x into px actually. Okay, so you look at the expression. So this becomes 11 minus 14, okay, into 0.5 plus 17 minus 14 whole square into 0.5. So this you have to calculate. You followed. So you calculate, this is very straightforward. So you will get the standard deviations as taking a square root, it will be 9 actually. Now in the second case, it will be simply 20 minus 14 whole square into 0.5 plus 8 minus 14 square into 0.5. So this turns out to be some 6 actually, the standard deviation. The variance will be 36. Variance will be square of sorry, this is 3. I'm sorry, the variance here is 3. Okay, sigma x square is 9. Okay, whereas here also sigma y square is the 36 will come. So these are the individual variances, individual means. Now I want to find out the covariance. Now how to find out covariance? So how to find out covariance? So to find out covariance is what is required? Individual things are easy. Okay, now to find out covariance, what you have to do? And let us say if they are if they are dependent, now what will happen? Now, if they are dependent, what you have to find out? Now, what is the first step we have to do? Just now we told you, right? So for knowing the one-dimensional things, can you find out to find out covariance, what you require? You have to calculate this integral. So to calculate this integral, so you require, what is that you require? To find out covariance, what is that you require? I have written, right? Now you require
intersection of
joint density you require. You followed the two-dimensional density function is required. Now here what has been given to you? You have been given two individual things. So now you have to construct a joint density. So let us say we have done. So now to construct the joint density, now you have to find out the sample space. What is the sample space now? Last class we have solved that problem, no? So two things are there. What is the sample space? How many possibilities are there for this discrete case? Individually, two are there. Now when I combine, say, what is that we get? How many are there? 4. 11 and 20, 11 and 8, then 17, 20, 17, 8 basically. Okay. So now my sample space will be 11, 20 is one combination. 11, 8 is another combination, then 17, 20 is another combination, then 17, 8 is another combination. So my sample space consists of this one. Now for the simple problem, say, I will assume some simple thing. I will say that probability of this this is 0.5, this is 0.5, and this is 0, 0 actually. So this is my joint density function. Just for simplicity, we have done like this. So this is 11, and this is you followed, right? 17. And then this one will be 8 and 20. Okay, so what we are trying to say is this combinations 11 and 20. So this is 0.5, then 17 and 8. Okay, so this is 0.5. All others are 0, 0, 0, 0 kind of thing. Okay, so this is my joint the density function or whatever for this problem. And now you calculate covariance. Now what will be the covariance here? Now, what will be the covariance? So now among these 4 combinations, say, okay, so this is also you have to sum up over all 4 combinations. Now advantage for you is how many combinations are having 0 probability?
2.
Only 2, and only 11, 20, 17, 8 only have non-zero probability. So now if you sum up, okay, so finally 0.5 this comes up. So you will be having 0.5 into 11 minus 14 multiplied by 20 minus the 14 kind of thing, because means are also same, say individual means. 0.5 into 17 minus 14, and then 18 minus 8 minus 14. Okay, so you calculate this number. So this turns out to be minus 18 is the covariance actually. So now in this problem, so what is Rxy correlation coefficient? So covariance is this one. So sigma x was 3 and sigma y was 6 actually. So what will be this one? Minus 18 divided by 3 into 6. What is the value?
Minus 1.
-1.
-1. So what is that physically trying to tell you? Rxy is -1. What is your comment about these two random variables?
They are not at all like good. There is no good correlation between these pairs.
See, what did we say? When Rxy will be -1? We said, right, it can be plus or -1. So generally negative is related to you followed. So what? So what is that? If it is +1, what is your comment? The correlation coefficient is like a slope actual. Okay, it depends on this one. So if it is a negative, means what it tells you, they are negatively correlated. You followed. It is not that they are not correlated. So what does it tells you physically? So if there are negatively correlated, say, so if x is increasing, what will happen to y?
It will decrease.
It will decrease actually. Suppose if the correlation was a +1, say, then if x is increasing, what will happen to y?
Y also will increase.
So that means negative or positive, say both of them are highly correlated. One way is it is going the opposite direction, but other way you followed. That's what the important you see the the thing which you can identify from the simple example. Okay, simple Bernoulli random variable two-dimensional. So how to compute these numbers? Okay. So anyway, this is how the very interesting things comes up. So there are like if you see finance, is a stochastic finance, like mutual fund theorem and many theorems are there. Okay, this I have not told you what are these X and Y. So basically what this is something like you can assume this to be one company, say this also is another company, say. Okay, so which can take value from here and here. So how these numbers looks like. Okay, that's how things goes away. So I will not go into detail, but if some of you are interested, say there is what they call as mutual fund theorem. Some of you may be investing, we also do. So the share market and other things to say. So all these theorems and other things, they're all based on this covariance, the total returns, like for example, generally when you are investing money, say you will invest not in one share, like you are investing in several options. Okay. So how to maximize your returns? How to maximize this one? So the covariance between these two shares and other things becomes very, very important in finance, of course, even in our civil engineering also, but it is very people they use it very well in finance. So there is a theorem is there, you can go through net and portfolio theory, they say. We will not go into detail. So if some of you are interested, say Markowitz portfolio theory. Okay. So there are very interesting things are there. Okay, so like you see, if I am if there are shares are there, say, so these are all the shares. I am investing in n number of share. Okay, so my total return basically will be the weighted average W1 into R1. How much money we have put on all these shares. So the question will be, what will be, I have to maximize my output actually. Okay, so the max, so now the L&T share, many companies say, if you see their data, you can calculate their mean value, you can calculate their standard deviation. So knowing that one, so I want to find out to say maximize my return set. So this covariance and others, people use, and these theorems are derived. Okay, so anyway, we'll not go into detail. If you are interested, you can go through this theories itself. So fine. So now, so now here also we can have some examples we can give. So I can give them the example of a Bernoulli random variable for 2 dimensions. So now you can have the 2-dimensional Gaussian distribution also. And these are very special, the distribution, 2-dimensional. Density or whatever, this function. So if I have 2 random, the density function, you can write like this. Okay, so 1 by, it is a very big, the expression. So 1 by 2 pi will be there, sigma x, sigma y, then 1 minus r square xy, the correlation coefficient will be there in the denominator, and exponents say. And e to the power of, we have this big expression, minus half x minus mu x whole square by sigma x square. Okay, so it is inside this expression, plus y minus mu y whole square by sigma y square, and minus 2 times rxy, x minus mu x, y minus mu y by sigma x, sigma y. So this is the 2-dimensional Gaussian distribution actually. So now how many parameters are there if you count? See, 1-dimensional Gaussian distribution, we have only mu and sigma. Okay. Now, since it is a 2-dimensional Gaussian distribution, say how many parameters are there? Now, what are the parameters here in this expression? Now, count how many unknowns are there except apart from x and y. X and y anyway they are variables. Now, what are the unknowns? How many parameters are there?
4, sir.
What are those 4?
Sigma x, sigma y, and mu x, mu y.
Mu x sigma x, then mu y sigma y. Apart from that, nothing is there.
Rxy is there, but
XY, sir.
No, Rxy also is there. Rxy is there, but Rxy doesn't depend. What is the value of Rxy? It can be
So it
anything, right?
depends on sigma XY.
So it depends on how X and Y are related. If X and Y are linearly related, say, then you can have plus or minus 1. You understand? Suppose if X and Y are not related in a linear relationship, say, then Rxy will not be equal to 1. So it will be something else. So total, how many parameters are there? So total it is 5, not the 4 are there. Now here one very interesting the information comes here. Now in this two-dimensional case, if Rxy, if it is 0, what happens? Tell me. Now what happens to Pxy x comma y? You substitute Rxy 0 in this expression and then tell me what you will get. Now what is your observation? That means correlation coefficient is 0. Now what happens to this expression? Now, what is that you will observe here when Rxy is 0? What happens to this expression? So in this exponent, this term becomes
0, sir.
0. Now here also in the numerator also you have Rxy. So this, if it is 0, say, so this entire expression goes away. So you will be having x minus mu x and y minus mu y will be there. So now how do you write this expression if you split into two things, say? If I split into two pieces, what happens? Now substitute, if I split this into, so this also, if I write this as root 2 pi into sigma x, then root of 2 pi into sigma y. Anyway, the square root, when you multiply, it goes away. So this also I can split into two pieces in the numerator. And this also, I will have this separate and this is separate actually. What do we get? What is 1 by root of 2 pi sigma x multiplied by e to the power of minus half x minus mu x whole square by sigma x square? Now what is this? 1 by root of 2 pi sigma x e to the power of minus half x minus mu x by sigma x whole square. So this is one quantity. Similarly, you have 1 by root of 2 pi sigma y, same expression mu y by sigma y whole square. Now what is this? This is nothing but, now what is this quantity? This is nothing but
Gaussian distribution of X into Gaussian distribution of Y.
Excellent. Gaussian, that is a one-dimensional distribution. You followed Px of X into Py of Y actually. You followed. So what is the most important thing we have seen here? Now, so for Gaussian distribution, say two-dimensional Gaussian distribution, if the random variables, if they are not correlated, if the correlation, if it is 0, say, what do you call this property? Now, when you can write the joint density as a product of one-dimensional things? Now, what do you call this? Then what is that we say? X and Y are? If I can break down a joint density into two separate pieces, a multiplication, P of A intersection B is P of A into P of B. Say, what is that we are trying to tell us? What is that it means?
They are independent.
They are independent actually. So now for Gaussian process, okay, for Gaussian two-dimensional Gaussian process, when independence is guaranteed, independence depends on
Correlation.
Rxy. So for Gaussian, this is a very important property of Gaussian distribution, two-dimensional Gaussian density. If X and Y are uncorrelated, say, so automatically the random variables will be independent because the probability density function can be written as a product of their individual things itself. So it's a very important property of Gaussian distribution. And of course, it is valid only for Gaussian only. Suppose if it is not Gaussian, if it is something else, a complicated distribution, then this may not be true actually. Okay, uncorrelatedness doesn't mean the independence, but uncorrelatedness means independence. This property is only valid for Gaussian distributions. If you want to check for other distributions, say, so you substitute Rxy 0 and then you have to verify this property, but it doesn't happen. So this is a very special property of Gaussian actually. Okay. So this is a very special property, like this uncorrelatedness. Okay, uncorrelated means it is independent. So this is a very unique property of Gaussian distributions. Okay, so this one, so this is how you see. So like this, there are several others are there. When we will go into two-dimensional things, when when we discuss some practical problems, or when we go into the reliability theory itself. Okay, and now let us see one more important thing: functions of random variables. This is also anyway related to this two dimensions. Okay. Yeah. So this is also very interesting. So now let us have x. Its density function is px of x. Okay, and I have y, a new random variable which is a function of x. Now what will be py of y? Okay, this is my question mark. So how to find out this quantity, this one? So as already we said, right, this is what essential in reliability or whatever. Okay, so like for example, if I have a cantilever beam, say, okay, so I know the deflection. So PL cubed by whatever 3a or whatever you have this one. Now let us say given that load is random, say, okay, load is random and it has some probability density function. So now I want to find out the density function of delta, okay, which is a function of P itself. So how do we calculate this expression itself? Okay, so like you see, for example, say, let us say x is a px of x and y is x square. Okay, so now what will be py of y? So how do we calculate this expression? Okay, so now if you see the distribution function of y, say, okay, so I can write this as p y less than or equal to y. Okay, this is same as saying y is x square. Okay, x square less than or equal to y itself, or I can also write this expression as x less than or equal to square root of y itself, which is nothing but the probability distribution function of x, say, up to root y, or this I can write this as 0 to root of y itself. So this is you follow, right? So px of x dx kind of thing. Now let us say px of x, say the density function is given as some 3x square, and x lies from 0 to x less than or equal to 1, say. Okay, so you can find out py. So you substitute this in this expression, so I can have 0 to root of y, so 3t square dt. So substitute and then you do the integral, right? So you will get this as y to the power of 3 by 2. So my py of y, say the density function. So you have to take the derivative of the distribution function. So 3 by 2 times root of y, and of course y lies from 0 to 1. So you can estimate from your x itself. Okay, so this is how we calculate these functions of random variables. So you use the same expression, but you have to do it in a special the format itself. Okay. So now so let us let us generalize this statement. So if I have x, okay, so which is a px of x, and y is some u of x, okay, and you can do the inverse also. That means x is v of y also I can write. You follow? So now py of y we want to find out. So this means p y less than or equal to y. So this means p u of x, say, less than or equal to y, or the same expression is the same as x less than or equal to v of y. You follow the same expression. So we are writing instead of this is in the density function for y, this is in terms of x itself. So because x and y are all of them are correlated, they are interlinked, this one, it is same as writing this expression. So x less than or equal to v of y becomes minus in 0 to this v of y, px of x into dx. Okay, so this is how we calculate this one. Now the density function, say, so this is a distribution function. I think I made a mistake. Is a capital P. So now the density function will be py of y. So this will be derivative. Okay, so dou by dou y integral 0 to v of y px of x dx actually. So this is my density function. You follow? So these are deleted. Now how do you evaluate this type of derivative? So you can see these are special things in mathematics. Okay, so you have to differentiate a function. inside things are all functions of y, okay, but the y comes only in the limits, upper bound or whatever this happens. So in mathematics textbooks, if you see Kreyszig and other one, there are some formulas have been given. So if I have any function, say d by d of x, f1 of x, then f2 of x, and then inside quantity is g of t dt. Okay, so the value of this integral will be, so g of f2 of x and f2 dash of x minus g of f1 of x, okay, multiplied by f1 dash of x itself. So this expression you see given in the textbooks. So using this expression, say, so this also if I try to calculate, so py of y, now the density function of y will be px, okay, inside v of y, and then the derivative of v dash of y. Followed. So this f2 fx here v of y is expression is here. So we write in this format actually. So these is how we obtain the density functions of the y. So if I know the density function of x, and if I know the density fund, if I know that function also y is equal to that g of x or whatever the transformation also, if I know, I can find out from this expression itself. It's a straightforward expression only. Okay. So now to have a clarity, so let us see. I have a function p of x of x, the distribution. So 3 into 1 minus x whole square, and y is given as 1 minus x whole cube. Okay. So if you try to reverse it, so x becomes as 1 minus y to the power of 1 by 3. Now what will be py of y? So I think I'm sorry, this is px of x, the density only. Yes. Now, so now what will be this value? So density function of x is given. The relationship also now what will be py of y? So use this expression. Calculate and tell me. So you work it out. You calculate and tell me what is the value. You can easily find out, right? V dash of y also. So you find out. Now what's the value? So px, what will be v of y? 1 minus y whole to the power of 1 by 3. And what's the derivative of v dash of y? So this has to be differentiated.
Answer is 1.
It is 1. So you take modulus, and finally this turns out to be 1, and y also will go from 0 to 1. Okay, so it's a straightforward kind of thing. Okay, so just you are trying to find out this expression itself. Now in a similar fashion, say this is a very interesting thing. So px of x, now this is a very important thing. X square by 3, and x varies from -1 to x less than 2, and y is x square. Now what will be py of y? Okay, so this is a question. Now here the problem what you are having is x lies from. See, now if I try to plot the graph, okay, I think I will do it here. So now if I try to plot the graph of y versus x. Now what is the relationship between y and x? Now relation is square of this one, and of course x is running from -1 to 2. So if I take this as -1 and this as +1, say, and let us say this as 2, y is equal to x square. If you try to plot it, this graph, how does it look like? So it goes like this actually, basically. So it is defined from this place to this place. You followed. So this is how the x square, y is equal to x square looks like. Okay. Now what we know is, we know the probability density function of x. So that graphically I am just showing you. So this is same as x, and this is a px of x. So let us say Px of X is some function, say it may be normal or whatever, it goes. So the probability density also, it is defined, up to here only. Now let us, I'm just drawing just a sample, okay. So something, you have here. And now we want to find out probability density function of Y. Okay, this is my Y. So I have, this is a Py of Y. And this is my Y. Now you tell me Y runs from where to where? Y runs from where to where?
0 to 1.
0 to 1. So X goes from, this expression X goes from -1 to 2, but whereas your Y runs, say, from 0 to 1. So these are the limits for Y. Okay. And now what is happening here? Now suppose this is the probability density function of Y. So I am trying to find out the value. So in this region, say from 0 to whatever this, this one. So I'm trying to find out this integral. Okay. So this area under the function, if I'm trying to find out. And now if I try to draw here, so what is happening in this region when X lies from -1 to 1? So what is happening? What is happening? This area I have to find out. So Py of Y, this is what I'm interested. So I'm projecting this into the this map and then projecting onto the probability this function. So now what is happening? Tell me. No. So Py of Y, when X is from -1 to 1, how many areas you have to add? See how many areas you have to add. It is projecting to how many areas? When X is from -1 to 1, this region. Suppose if I try to find out in this region, say, what is happening in this region? It is getting projected to how many points are there? See, for a given Y, how many X are there in this region from -1 to 1?
2.
So when X lies from 1 to 2, say, how many regions you have to project?
1.
Only one is there. So now this calculation, say, so now you have to do twice here, whereas here. So now you can do -1 X less than or equal to 1. So this is one interval because you have now the roots will be X. What are the roots? So Y is equal to X square. What is X? What will be the X when X will be when Y is X square? So what will be this one? Now what is X? X is equal to when Y is X square. So what will be X? This square, if you try to pull it other side, so what happens? You will get it. Now tell me, Y is X square. What is X? X is
Square root of Y.
Here you have to be careful. It will be plus or minus. You follow? So, this you have to be careful. That's why you are having these two roots actually. So you are having two roots. One is minus root of Y and another root is plus root of Y actually. Follow? So two roots. So this will be V1 of Y and this will be V2 of Y actually. Okay. So now your Py of Y, say. Okay. So this I can write as P of X. The first root is minus root of Y and then a derivative you have to do 1 by 2 root of Y plus Px of root of Y multiplied by 1 by 2 root of Y itself. So this turns out to be root of Y by 3, 0 less than Y less than 1 itself. Now when 1 is less than X less than 2, say, so then there is no issue. X is root of Y only because there is no root, on the other side. So now my P of Y, say, so this will be, so Px of root of Y and then that modulus V dash will be there. So 2 root of Y. So this turns out to be root of Y by 6 actually and Y less than 4 actually because Y is X square. So now my probability density function of Y, say, can be written like this. Root of Y by 3 when 0 less than Y less than 1 and this is root of Y by 6 when 1 less than Y less than 4 actually. So this is our probability density actually. So this you have to calculate very carefully. Okay, it's not just the straightforward this expression, but you also have to look at, you see how many roots are there, where it is a cutting, and then you can find out this numbers itself. Okay. So anyway, so I will stop here. We'll continue in the next class. If you have any questions, you can ask me. And another thing is, I will send you the assignment also. Maybe by tomorrow, you will get the assignment.